In our proposal, we utilise carbon dioxide to identify far better ways to decarbonise the transport sector, produce decarbonised electricity and improve the UK's energy security. We do this through more effective utilisation of pre-combustion capture technologies. In existing processes, natural gas is split into carbon dioxide and hydrogen. The hydrogen is burnt to produce electricity. In our proposal, we utilise the synthesis gas stage to produce methanol, a valuable product, and CO2 for enhanced oil recovery. We add significant revenue streams and increase the flexibility of the power station.
Our proposal does not burn methane, it takes natural gas from the North Sea.
We then make carbon dioxide profitable by using it in enhanced oil recovery schemes and combining it with hydrogen to produce methanol.
We burn most of the hydrogen in a power station to produce decarbonised electricity. In existing carbon capture and storage projects, revenue comes from carbon trading credits. These are very volatile. In our proposal, we introduce other revenue streams to the plant. Through utilising the equipment in place, we can produce methanol, and we can also use carbon dioxide for enhanced oil recovery. Through doing this, we are selling known products to known markets, and hence, overall, we are reducing the risk to investors. The implementation of this approach would lead to the construction of more CCS plants than the 4 plants UK government have planned for in the UK.
Methanol production, electricity generation and carbon dioxide for enhanced oil recovery will all generate revenue. Take the carbon dioxide, inject that waste product into the North Sea oil reservoirs, you'll win an extra 3 billion barrels of oil.
EOR typically increases the available oil in a reserve by 10%, with every tonne of CO2 producing about 3 barrels of oil. This equates to about 4,000 barrels of oil produced daily at each power station. Because EOR is only available in the northern part of the basin, more CO2 for EOR will be produced in power stations in the north of the UK, with southern power stations producing more methanol or storing more CO2. EOR schemes in the north build infrastructure which can later be used for CO2 storage.
The carbon dioxide and the hydrogen produced from the plant can be combined to form methanol. Currently, around 40 million tonnes of methanol are produced globally each year. In our proposal, around 1/3 of the carbon dioxide will be used to produce around 500,000 tonnes a year, which is similar in size to the plant shown, which returned $200 million in 2008. We would initially use methanol as a chemical feedstock for products such as formaldehyde and acetic acid.
We're here at Lotus to find out more about using methanol as a future transport fuel.
On an energy basis, you could make a car much more efficient if it runs on an alcohol than you can either gasoline or diesel. It's actually going to be cheaper to convert to another liquid fuel. You can make the same distribution network still carry the fossil fuels in the transition period. You can turn methanol into kerosene or diesel with a further 10% energy loss, but you can still provide the aircraft and the ships as well.
So what does all this mean we've got here? It's a tri-fuel car, and the reason we've been doing it is to look at alternative fuels and the roles that they may play in the future in a world in which we face increasingly difficult problems with CO2 and energy security.
We created an economic model for one of our proposed plants and used government investor forecast data for costs of carbon credits, gas and electricity prices. We incorporated the capital expenditure of methanol and CCS plants, as well as the operational expenditure and tax. In this model we have shown that our plant will become profitable by 2019.